Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World. Today's event, Fundamentals of Spectroscopy and Imaging Spectrometers, will be presented by Sebastian Remi, Application Scientist at Princeton Instruments. This presentation is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. And I will be holding a short Q&A session after the presentation, and I encourage you to ask questions anytime during the presentation. A PDF of this webcast is available in the Resource tab right below the question box on your screen. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's speaker, Sebastian Remi.
Thank you, John, and thanks for attending the webinar today, everyone. So let me first tell you who we are, Princeton Instruments. Princeton Instruments is a supplier of cutting-edge scientific equipment for imaging and spectroscopy experiments such as spectrographs, CCDs, or CMOS devices. We are operating worldwide, but we manufacture our equipment in our factories in New Jersey and Massachusetts here in the US. Our core technologies focus on the following areas. So our main staple are innovative scientific cameras ranging from a large wavelength range from the X-ray range to the IR. In particular, focused on very low noise performance that typically require high cooling capabilities. That includes, as I mentioned, CCDs, SCMOS cameras, EMCCDs, as well as intensified cameras and indium gallium arsenide devices. Another area we focus on are advancing the state-of-the-art in spectroscopy, mainly in the recent past by introducing aberration-free spectrometers. We also provide innovative software for data acquisition and analysis, as well as working in providing optical elements for application and optical coatings, knowledge that helps us greatly to optimize also our camera and spectroscopy products. But long story short, let's move on to the topics of today's talk. So in the first part of the webinar, I will discuss, give a light discussion of what spectroscopy is and why we do spectroscopy. Spectroscopy is a very wide and extensive field, but it's nevertheless useful to understand why we do it and what information knowledge we gain from doing spectroscopy, as well as what information we gain from observing spectra. And I will present a few practical examples. So in the second part of the webinar, I will talk about specifically imaging spectrographs, as they are widely used in doing spectroscopy, and discuss some cases we practically discover often in the field, mainly how to get light into a spectrograph and what effect aberrations in the instrument's response have on experiments and observations. So let's talk about spectroscopy. So generally speaking, spectroscopy is the investigation of matter using light. So in the simplest example, I might just understand this is just looking at an object, detecting light with my eyes. Typically, I mean the analytical study, how materials react when being exposed by light of different color or how they emit light. So I find it interesting to just take a brief look backwards and discuss some history, as spectroscopy has been very closely tied to scientific advances about light and materials. So this list is by no means complete. It's very selective. But I thought it's worthwhile to go through it in any case. So the beginnings of spectroscopy, I would date back to Isaac Newton, who discovered that white light is built up of several colors by observing white light, diffraction of white light on a prism. So ever since people looked at the spectral output of light in spectra, in around 1800, and so the theories of light and elements became to form in the 18th and 19th century. Around 1800, Fraunhofer and Wollaston observed dark lines in the spectrum of the sun, which could be seen as the beginning of spectral analysis, and it later turned out that those lines can be attributed to specific elements that are present in the sun's atmosphere. For example, it's interesting to note that helium, for example, was first discovered in the spectrum of the sun in 1862, even before it was synthesized on Earth and discovered on Earth, some 20 years after discovering the sun spectrum. In the mid-19th century, Bunsen and Kirchhoff were probably the first ones to perform really quantitative spectroscopy, and mainly discovered that different elements have a unique spectrum, so really used spectroscopy as a tool for elemental analysis. Also in the 19th century, the picture of light is being formed of electromagnetic waves was put on a solid footing by Maxwell and many others. At the beginning of the 20th century, Planck explained the black body spectrum, and it's kind of the birth of quantum mechanics, and that was heavily based on spectroscopic observations of thermal radiation from black bodies. Quantum mechanics, of course, is still the fundament of all our understanding of how light and matter interact. Going further, one point that stands out is then the Bohr model of the hydrogen atom that explains the observations, spectral observations of and where the spectral lines are located. Moving forward, like in the very recent past, significant discoveries were the invention of the laser and scientific detectors in the 60s that really boosted the applicability of spectroscopy. So one can see, like historically, advances in spectroscopy are very naturally coupled to advances in our understanding in physics, chemistry, and many other areas. So today, spectroscopy is one of the widest used analytic techniques in physical and chemistry, biological sciences, with applications ranging from astronomy to nanotechnology. So what do we learn specifically from doing spectroscopy? So a few things are learning about the inner processes of matter, molecular structure, identifying and fingerprinting materials, determining the chemical composition of materials, be it in the lab or on distant objects, be it stars, or the Mars rovers have instruments to spectroscopically identify materials. Industrial quality control, either in the food or pharmaceutical industries, is an area where spectroscopy is used. Investigations of dynamic properties of atoms and molecules, like in time-dependent measurements. Spectroscopy can help to determine temperature of an object, and in general characterize and understand chemical and biological processes, like chemical reactions, for example. So what is light? So it is known that light is an electromagnetic wave, and it is mainly described by and characterized by its wavelength. So in the visible, the wavelength determines the color we see of light, and the wavelength is the distance between two maxima in the electric and magnetic field oscillations. Light also carries energy, and energy and wavelengths are related by a simple inverse relationship. So energy is equal to Planck's constant, h, times the frequency, or that's Planck's constant times the speed of light, h times c divided by the wavelength lambda. So radiation of very short wavelengths will have very high energy. Radiation of very long wavelengths will have very low energy. Also, an important property of light is its polarization. So it's mainly the direction of the electric field vector. So polarization can be important because either spectroscopic processes depend on polarization, and as well as most optical components in optical instruments used have some polarization dependence as well. So here we see the electromagnetic spectrum, and modern spectroscopy really extends through all ranges of the electromagnetic spectrum. So on the low energy side, there are radio waves and microwaves. Microwaves mainly target rotational modes and molecules. In the infrared, we can observe vibrational modes of molecules. And the main area where we also use dispersive spectroscopy to investigate light is from the infrared then into the visible and UV. In the visible and UV, that's mainly atomic electronic transition in atoms we observe in the outer shell of atoms, and moving to even higher energies, X-rays, are produced by electronic transition in the lower atomic shells, and in atomic nuclei, observations are done in the gamma range of the electromagnetic spectrum. So it's a really wide range that is covered with applications. So the light, where's the light coming from, and what happens when light strikes matter? So the two main processes, very simplistically speaking, are either absorption, so that's a photon hits an atom, the photon is destroyed and the atom is being put in a higher energy state, or emission is when the atom has been transitioned into a lower energy state and emits a photon. So this leads to various processes, either direct observation of absorbance, for example, or emission, let's say from a flame of a gas, various luminescence processes, so the high energy state might be produced by a biological or a chemical process or an electrical process. Photoluminescence, like fluorescence or phosphorescence, excite first an atom with incoming light, and then light of a different wavelengths typically is emitted. Raman, the Raman effect is inelastic scattering of light, and black body radiation is the thermal processes involved when looking at materials. So spectroscopy is, besides understanding the inner processing materials as well, it's also very useful because the energy states and in atoms as well as molecules depend often very sensitively of the environment. So I mentioned already that, for example, temperature might be able to observe, but things like the concentration in a solvent, for example, the interactions with other molecules in the environment is important. The chemical environment, what the pH or solvent polarity is, the electromagnetic environment, so be it external electric or magnetic fields. So spectroscopy, therefore, can be a useful tool to determine any of these quantities in a system that is being studied. So most spectroscopy experiments involve some form of a spectrometer to analyze the spectral or color components. And so very widely used, and that's what I focus on in this presentation, are grating-based systems. So on this slide shown is a type of spectrum that's called a Cerny-Turner spectrograph. Those are very popular because grating spectrographs of this type are very versatile and can be easily adapted to very many different experiment configurations, and it's a very established technology. So the basic components of the spectrographs are as follows. So light is first hitting an entrance slit, or often these days people use optical fibers instead or with a slit to bring light to the spectrograph. There's imaging optics. So first, typically the light is collimated, and then it hits a dispersive element. So in the Cerny-Turner spectrograph, it is a diffraction grating. And then optics will focus the light on a focus plane or an exit slit, where it typically hits a detector. So these days, CCDs are very common, but also single-channel detectors are used, as well as kind of one-dimensional, like arrays of photodiodes, for example. So what we observe as output is a spectrum. And so a spectrum has on its x-axis the wavelength or energy that is being detected at, and on the y-axis is some form of intensity, be it like typically something proportional to the number of photons at this wavelength that hit the detector. So spectra have continuous or sharp spectral features or spectral lines, and once the spectrum is acquired, the task is to analyze what the position, height, or width of these features are to extract information from them. So let me discuss a few very simple examples of spectroscopies. So the first one is absorbance, which is one of the most basic technique. So for an absorbance experiment, it's very easily set up. So you use a light source. In this case shown here, the light of the source is brought with a fiber to a sample cell with a solvent. The light passes through the solvent, is collected in another fiber that is being connected to the spectrograph. The light is being compared to a reference spectrum, like with only solvent or solvent with a sample in it, so that the system can directly output the absorbance, like how many % of the light at a given wavelength are being absorbed. The typical analysis in absorption experiments uses Beer's law. So that is, the absorbance is proportional to the wavelength-dependent extinction of the sample, the path length, and the concentration. So in particular, when the extinction coefficient and the path lengths are known and constant, that's an established way to measure concentration of a substance in a solvent, or even partial concentration in a mixture. The next example is Raman scattering, and we keep it very basic, so a whole other presentation could be made about these techniques. So Raman spectroscopy observes inelastic light scattering and typically uses lasers for excitation. The Raman light is inelastically scattered, so it's shifted in energy from the laser and finally being detected. So a basic setup therefore looks as follows. The laser hits a dichroic mirror, and that is reflected to the sample in this case. The dichroic mirror will reflect the laser light, but the energy shifted Raman light can pass through the mirror where the laser is blocked. That's important because typically the signal is very weak in a Raman experiment, and so the laser signal would overwhelm the light. Finally, the light goes through a coupling lens into the spectrograph. And so here is what one might observe. These are Raman spectra of different substances. So there's cyclohexane on the top, sulfur in the middle, and some ibuprofen on the bottom. There might be some contamination kind of in the ibuprofen. That's why it has a pretty large background, but nevertheless you see discrete lines. Oh, I'm sorry, forgot to switch the slides. So cyclohexane on the top, sulfur on the bottom, ibuprofen on the middle, ibuprofen on the bottom. So you see discrete lines, and one can easily see that those lines are different for any material. In fact, those are unique identifiers for materials. So Raman is very widely used for material identification or probing if materials are contaminated, and that is the reason why. So let's look more into the instruments that are used to acquire the spectra. So I've already mentioned that grating spectrographs are widely used, and often these days instruments use two-dimensional detectors like CCDs that are capable to detect a two-dimensional image. For example, here is one can see an image of a fiber bundle on a CCD. So there's extend in the Y direction as well as X, because they're different wavelengths going through the fiber bundle, so it's detected at different places on the detector. So in fact, all spectrographs are imaging instruments, no matter what the detector is in the end, even if one uses a single channel detector. And ultimately, the performance is typically limited by image aberrations or the instrument-specific kind of response to the spectrum. The basic principle of an imaging spectrograph, and we observe often that this is not clear to users of these instruments, but is as follows. So one has some input object. This might be an illuminated entrance slit. In this case, there's an image illuminated with a mercury lamp, and the light passes through the detector, through the spectrograph, and is split into its spectral components. And what is seen on the detector now is basically a convolution between the spectral content of the signal and the input image. So in this case, with a real image, we see kind of versions of that image at each of the spectral lines of mercury. Here we go. Each spectral lines of mercury. So my apologies for switching the slide slate. So let's just rewind. So here the image, you see at each of the spectral lines of mercury a version of the image. To gain a resolution, one would simply close like an entrance slit to get like sharp spectral lines. So when one does that, so here is how we gain spectral information then from these images. So basically one goes from the two-dimensional image. So here's again a fiber bundle with different wavelength content. And so we can simply by vertical binning of the signal, that can be either done in hardware so that the signal on the detector is added together, or after reading out the detector and one recovers the well-known spectrum with spectral lines. So, but why would we use imaging spectroscopy? What are the advantages for using imaging spectroscopy? So one advantage is that it might enable one to collect more light at many wavelengths simultaneously, simply because one can use a higher detector. Also, in the case of the fiber bundle, it's easy to collect several spectral channels simultaneously, like each of the fibers might lead to a different point in the experiment. That can increase the number of observables greatly in the experiment. So two examples are Fourier plane spectroscopy that collects wavelengths and on the x-axis as well as momentum information on the y-axis simultaneously. Another example is hyperspectral imaging that collects spatial information on the y-axis. Together with the spectral information at each point. So an example of hyperspectral imaging is microspectroscopy. So the setup can be very simple. So basically one attaches a spectrograph directly to the output port of a microscope. And in this case, we observe an image on the of like a cell. By closing the entrance slit of the spectrograph now, that is kind of shown by the red line in the image, we select a region from where we obtain spectra. And from each spatial point underneath the slit, one collects now a spectrum simultaneously. In this case, depending on the location and the composition of the cell at each point, there are different output spectra, and by spectral analysis, one can produce beautiful-looking false color images that highlights kind of different functional elements of a cell, for example. So this technique can be very powerful. The basic question that we get often asked is, so how we get light into a spectrograph. So this complex image is taken from a paper called Imaging Spectrometer Fundamentals for Researchers in the Biosciences by Jeremy Lerner. And it shows the kind of illumination and imaging train of a spectroscopy system. The parts that are within the spectrograph are within the blue frame. So there is a sample to the very left, marked with S, that has some extent and emits light under a certain angle. It hits like an aperture, typically like an imaging optic, for example, and it's focused on the entrance slit of the spectrograph. There are like various then elements we described before, the collimating optics, the dispersive element, the focusing opposite, and finally kind of the exit aperture, and where typically the detector sits of the spectrograph. So what needs to be taken care of to optimize this? So an important concept to understand is the aperture of a spectrograph. So the aperture is the spectrograph is the ratio between the focal length and the diameter of the limiting aperture in the system. So in the spectrograph, it's typically the mirrors. The aperture typically decreases with focal length, and the way this is important for coupling light in is that the light gathering power of a system decreases with lower apertures, and I will present some more examples of that in just a little bit. Typically aberrations in spectroscopy, we will see that in a couple of slides decrease with aperture as well. So here I listed the aperture ratio for a few commonly used focal length spectrographs. F over for systems like the 300 nanometer focal length, and compared to 500 millimeter focal length system with which is an F for 6.5 system. The F over 4 system has about twice the light gathering power of the F over 6.5 system. So as an example where aperture directly plays a role, let's consider coupling light into the spectrographs using an optical fiber. So fibers typically have a specific numerical aperture as well that define the acceptance and emission angles of light. The F number is related to the NA, as F number equals 1 over 2 times the numerical aperture. A very common value for fibers uses F over 2, and so in the image here, it's an F over 2 fiber that's about to be connected to a F over 4 spectrograph. However, the input aperture of the spectrograph would be greatly overfilled in this case, and because the aperture of the fiber is significantly larger than the spectrograph, and in this case, about 70% of the photons would be lost as they are connected to the spectrograph. The typical best approach is to do F-number matching. So that means matching the F numbers of the coupling optics to be within the, or to match the F number of the spectrograph, so that the acceptance angle matches the best collection angle for the spectroscopic instruments. And we see very often that this is not being properly taken care of or optimized in many situations. One thing to take care of, while F-number matching is typically the right approach, one has also to take into account the magnification of the light source on the entrance slit. So typically it's the recommendation is to work with the widest possible slit width that still allows you to achieve the resolution you want in your experiment. So in spectral resolution is the next part I wanted to mention. So that's one of the main measures of the power of the performance of a spectrograph, and it characterizes the ability of the spectrograph to distinguish two adjacent spectral peaks. So there are many parameters that the spectral resolution depends on. So typically the spectral resolution changes with the wavelength observed. It changes with the groove density of the grating that's being used. So higher groove densities have higher dispersion and give you higher resolution typically. A higher focal length spectrograph has higher resolution. The entrance slits width and height can change the resolution. The aperture ratio. influencing the point spread function in particular. So the point spread function, and we talk about this in a second, measures the response of the imaging system. The size of the pixels of your detectors, as well as the order you observe. So for most grading spectrographs, you observe in first order. So typically that is constant. But you might be able to observe spectral lines in second order in one of these systems as well. Ultimately, though, the resolution is determined by the instrument response. So as is illustrated in this image, so here is the spectrum of a monochromatic light source. So the real spectrum is a sharp spectral line, and in a perfect spectrograph, which is seen in the middle, that would produce a perfect spectral line. However, in a real-world system, that monochromatic light source will be broadened by the instrument's response. So we can measure and visualize the point spread function of the instruments, and fiber bundle can be a good point source and good source for that. So here is the image of a fiber bundle shown. So on the input side, it's like a circular kind of arrangement of fibers on the spectrograph side, and I showed a couple images of that already. They are arranged in kind of a linear pattern that is arranged to be vertical on the spectrograph. And so remember that output is a convolution of the spectrum. So here we use a multispectral lamp, like a mercury lamp, to produce the image, and the input image is reproduced at every wavelength. So in a nice imaging system, the picture should be broadened, but should produce a nice circular image at all points in the focal plane. However, that is clearly not the case in this image, because the image is distorted by aberrations. So this might be okay for like a single channel detector observations where you only collect signal in the center of the focal plane. But whenever you bin or look at a wider extent of the spectrum, the aberrations will lead to a decrease in spatial as well as spectral resolution of the spectrograph. So what can we do against that? So one way is to decrease the aperture to improve the imaging power. So this image shows, here you see the image on the detector at one of the edges. Here it's the right edge of the focal plane. And you see that at f/4, aberrations really distort the image so that it's barely recognizable. Whereas if the aperture is reduced, a nice sharp image can be reproduced. However, keep in mind that at the lower aperture, light collection power decreases. So at f/22, we collect only 3% as much light as at f/4. So one of the most common effects that's easily seen by experimenters is astigmatism. So astigmatism is caused by use of off-axis use of the optical elements in the spectrographs, and the effect is that images are elongated. In particular, once you go towards the edges of the focal plane, the elongation gets stronger and stronger. So that limits the spectral and spatial resolution. And in this case, where fiber bundle is used, you see how the spectral channels overlap and can't be used as separate entities. However, typically instruments are astigmatism corrected in the focal plane center. But in a certain Turner system, for example, they are only corrected in the focal plane center. So as soon as you walk away, you get distortion of your spectral signal. Coma is another aberration that is easily seen by users. So the cause is also use of mirrors to image off-axis source. Most importantly, as one can see in the spectrum, Coma produces these very asymmetric kind of tails to spectral lines. And so they are asymmetrically broadened in that way. Again, this will limit the spectral resolution of the spectrograph. However, Coma can be, in a basic system, is typically corrected, but can only be corrected at a single grading angle. So, like a spectrograph might be corrected for use at 500 nanometers with specific groove density grading. So why one can, oh, and I'm sorry, I forgot to let me revert back. So Coma, let's look at the slide once more. I forgot to switch them again. So here are the asymmetrically broadened lines. So another way to fight aberrations is by going to aberration-corrected instruments. And in the recent past, there have instruments been reduced that produce images with less aberrations while maintaining the aperture and the light collection power. So these new classes are, for example, called Schmidt-Cerny-Turner spectrographs or diffraction-limited spectrographs. And so here one sees a fiber bundle image produced by a Schmidt-Cerny-Turner spectrograph that is produces the images of a fiber bundle nicely across the whole focal plane. These systems can eliminate astigmatism and or coma at all wavelengths, so one can achieve higher resolution while maintaining kind of light throughput. So effective signal-to-noise of your signal can be increased that way. So after talking about aberration, last but not least, I want to quickly mention the spectral response of a system. So which is, I see that it's often overlooked and uncorrected in experiments, but can have significant impact of measurements. So for example, look at this image on the slide here. It shows the spectra of the same spectral lamp observed with exactly the same spectrograph, but with different detectors that have different sensitivity maximas. And you see the spectrum looks different every time. So what is the right spectrum is the question. In fact, all optical components in the optical system have a wavelength dependence in spectral response that can distort a signal. For example, diffraction gratings have a wavelength-dependent efficiency that is typically highest at the blaze wavelength of the grating, but then falls rapidly off to either side. The reflection coefficients of optics have a wavelength dependence. So I was explaining how different optical elements have different spectral response. So John, go to the next slide, please. I just wanted to illustrate that there
We're now on slide that says intensity calibration.
Exactly. Okay, we are on there. So, so intensity calibration is the method you use to use it. I won't go into too much detail. I just want to show the effects if it's done properly. So on the left, you see spectra. Taken from the same lamp, but with different instruments and different configurations, so they all look different. But if you properly calibrate them, they can be made to look the same way. So very often these days, systems have like, or spectrograph manufacturers have like hardware as well as provide like routines to do these things easily for the users. So you can talk to your spectrograph provider or manufacturer about that. So John, can you switch to slide 37, please? So this was my presentation today. Thanks everyone for the attention. Sorry about the few mishaps with the slides. I want to encourage you to visit us at princetoninstruments.com to check out our products and if we can help you. And I'm happy to answer any questions now in the Q&A. So back to John.
All right, we're now in the Q&A portion of the webcast. So to ask a question, click on the Ask a Question button in the presentation window. Our first question. Is the spectrograph still coma-corrected if the grading is changed to a different groove density grading?
Yeah, that's a great question. So spectrographs are, unless you have like a coma-free system, if your system is coma-corrected, to be corrected for a specific grading angle. So that might be for, let's say, a 1200 grooves per millimeter grading at 500 nanometers. If you switch to a grading with a different groove density, that has different diffraction power, so the diffraction is much weaker, so you would not have to, the grading at 500 nanometer would be at a different angle. So the grading would not be coma-corrected at 500 nanometer. However, a 600 grooves per millimeter grading would be coma-corrected around 1,000 nanometers. So.
Mm-hmm. How do you perform an intensity calibration? So, for intensity calibration, the most important piece of hardware you need is a calibrated light source. So you need something where you know the output, and so that might be either for most experiment, it's calibrated light source where you know the relative kind of output. For some experiments, you might need to do an absolute intensity calibration. And then there's, you basically collect a reference spectrum. You send the light from the light source through the system, collect a reference spectrum that you can then use to calculate the spectral response. So some systems can do that automatically and make that very easy, as it can be quite hard to get the details of this completely right. So, but basically, reference kind of well-known light source to characterize the system. That's how you perform it. Mm-hmm. What's the typical ratio of input to output power, or maybe the other way around, output to input power in a Raman experiment? You mentioned that it's very weak.
Yeah, so it is very weak. So, for example, in the Raman spectra I've shown in the presentation, I moved the gradings were moved so that the laser line is just not seen. And so, in addition to the dichroic mirror, a long pass filter was used, and each of those filters have optical density around 5 or 6. So there's like a million, most of the laser lights is filtered out like 10 to the power of 10 or something like this. So there's like billions of photons less in the Raman light. One aspect that's important is, various strategies to increase. So one strategy might be to go to higher laser energies. So Raman cross-section goes typically with the frequency to the power of 4. So the higher the frequency is, the more light you produce. But nevertheless, it would be very weak. Just to put this in relation, I said like 10 to the power of 10. Like on a typical CCD, 16-bit CCD, the dynamic range goes to 65,000 counts. So yeah, the laser would be pretty overwhelming. So.
Okay, I think we have time for, say, 2 more questions. We do have a lot more questions than that, so I do want to say that people who have sent in these interesting questions, they will be all going to Sebastian, and he will be able to later answer them via email. So in a Raman application, why would one use a near-infrared laser instead of a visible or UV laser?
That is a great question. So One reason why people use an IR laser, like be it 785 or 1064 as frequently used, is that many samples show fluorescence. And so this is one way to get around the fluorescence and not to have them interfere with your signal, so to be much more sensitive. The other region is, and so I showed how you can calculate the energy, how that's related to the wavelength, so it's inversely proportional. So Raman produces a fixed energy shift. However, spectrographs typically operate in wavelengths. So as I move the grating, I image a fixed wavelength range. However, if I use a longer excitation wavelength, the same amount of energy shift will be spread over a much longer wavelength range. So that can be a means of increasing the resolution of my Raman experiment, because now the same Raman lines is extended over more pixels on my detector. So those are two reasons I can think of.
And the final question is a quick one. Any fundamental difference between a spectrograph and a spectrometer?
That is a good question. I typically use the terms that this might be like a very technical thing. I typically use them interchangeably. So, I think it's typically very, very technical. However, it might be important. There's like various instruments come with various different names, and so there are they might designate that they're used for certain measurement techniques and things like this. I use the term spectrograph or spectrometer typically pretty interchangeably. So that might not be the traditional way of doing it, but that's this is like how I, in practice, typically refer to it. So.
Okay. Sebastian, would you like to make any closing remarks?
Just I want to thank everyone for being on. I had some mishaps kind of with changing slides, but I saw many people stayed on, so thank you for that. I hope you gained some new insights. And visit us or contact us for any questions. We're happy to discuss your experimental setups with you and see if there's any way we can help. Wish everyone a good day.
Okay, well, on behalf of Laser Focus World and Penwall Corporation, I would like to thank Sebastian Remi of Princeton Instruments for today's presentation, Fundamentals of Spectroscopy and Imaging Spectrometers. This presentation will be archived within 24 hours and can be accessed from the homepage at www.laserfocusworld.com. A reminder email message for the archive will be sent to registrants complete with a link to the archive. We thank you for joining us today and look forward to future webcasts.